Okay, now we're going to use these equations in this example here. So it says a solution consists of 20.4 grams of silver nitrate and 113.6 grams of water. First, we're going to calculate the mass percent or the weight percent, the molality, and the mole fraction of silver nitrate in the solution. You always want to establish first what is your solute, what is your solvent, before you begin the problem. So here we have silver nitrate and water, and so we're going to dissolve that silver nitrate into the water. So silver nitrate is our solute, water is our solvent. Okay, so we are going to take mass percent, the weight of silver nitrate, and that is 20.4 grams, divided by the weight of the solution. So that's going to be your silver nitrate plus your water. So 20.4 grams plus 113.6 grams. And then we're going to multiply that by 100 since it's mass percent. And that gives us 15.2% of the solution is silver nitrate. Okay, we've got mass percent. Let's do molality. So molality is new. Molality is a little m, and it is moles of solute divided by kilograms of solvent. Okay. So we have mass of our solute, but we don't have moles. So that's a pretty easy fix. We just have to use molar mass to go from grams to moles. So 20.4 grams of silver nitrate. Okay, and the molar mass is 169.88. So we're going to divide by that. And that gives us 0.12 moles of silver nitrate. So we have that. Now we just need kilograms of solvent. We have grams. It's 113.6 grams. So to change that to kilograms, all we have to do is divide by 1,000. So that gives us 0.1136 grams, kilograms of our solvent. So we're going to divide the two, and that gives us 1.06 molal. So the little m to represent molality. Okay. Now we're going to do mole fraction. So we're going to find the mole fraction of silver nitrate in the solution. So we're going to take moles of silver nitrate divided by moles of the entire solution. So we already have moles of our silver nitrate. We just calculated that. It was, let me write this out here. Okay, so the moles of silver nitrate were 0.12. We found that in the last problem. And then, so we're going to divide that by the entire moles of the solution, so 0.12. So now we just need to find the moles of water, which are 113.6 grams. And we want to divide that by the molar mass of water, which is 18. Okay, and that gives us 6.3 moles of water. So we just need to include that here, 6.3 moles, because again, this bottom part is total moles. So we divide the two, and we are going to get 0.0187. So remember, mole fraction does not have units because these moles just end up canceling. So it's just 0.0187. Okay, the next question says the solution volume is 117 mils. Calculate the molarity of silver nitrate. So now we're going to do molarity, which is big M, moles solute, divided by liters of solution. So you can go in between molality and molarity, but in order to do that, you need the density of the solution, okay? So that's a lot of times your word problems will provide that. But again, that's just so you can go in between molality and molarity. Okay, our problem tells us that the solution is 117 mils. So We just need to change that to liters, so we just divide by 1,000. So it's 0.117 liters. And we've already figured out the moles of our solute. It was 0.12 moles of silver nitrate. Okay, we divide those two and we get 1.03 molar. So there's the molarity of our solution. Okay, we've got another problem here for you. It says calculate the ppm, so parts per million, of a solution consisting of 2.6 times 10 to the negative 4th grams of sodium chloride and 100 grams of water. So again, it's important to find what is your solute, what is your solvent. So sodium chloride is our solute and water is our solvent. Okay, so for ppm, parts per million, we just need mass of our sodium chloride divided by total mass of the solution. So the mass of our sodium chloride is 2.6 times 10 to the negative 4th grams. And we're going to divide that by the total amount of the solution. So we're going to rewrite that down here, plus the mass of our water, which is 100 grams. Okay, and since it's ppm, parts per million, we're going to multiply that by 10 to the 6. So we get 2.6 parts per million is the concentration of our sodium chloride in waters. And again, parts per million and parts per billion are used for very dilute solutions. So, intermolecular forces play a huge role in determining whether your solution is going to form or not. The stronger the intermolecular attractions between solute and solvent, the greater the solubility. So if the solute is able to overcome their own interactions and form an interaction with the solvent, the stronger the interaction between the solute and the solvent, the more soluble it's going to be. So we follow the rule, like dissolves like. So polar substances dissolve polar, or polar solvents dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes. So it's really important that what you learned about how to find if a molecule is polar or nonpolar in chapter 8, you're still going to be using that here, like we talked about with chapter 11. So that's still going to continue in this chapter. Okay. So there's two different types of energy factors that affect whether a process is going to occur, whether it's favored or not. So basically, is the solution going to form? So we're just going to cover just a little bit here of entropy and enthalpy. We're not going to dig too deep into it, but entropy measures the disorder of the system. It's closely linked to the motion of atoms or molecules. And so if you think about it, gases, they're in constant motion. They are very disordered. So the entropy is very high in a gas. But a solid is more ordered, right? Those molecules don't move around. They're held in place, so it's much more ordered. So the entropy here would be less. Okay, so always think disorder, movement of those molecules, it's going to cause your entropy to increase. Enthalpy has to do if something is exothermic or endothermic. So if a process is exothermic, so remember exothermic means that it's releasing energy, then it is favorable. Exothermic processes are favorable. But if it's endothermic, where it's absorbing the energy or the heat, then the process is disfavorable. And I forgot to say this just a second ago, but if it's exothermic, you're going to get a negative delta H. Okay, so when we're talking about enthalpy, we're looking at delta H, and when we're talking about entropy, we're talking about delta S. So the more negative the delta H, that means it's exothermic, that's favorable. And the more positive the delta H, that means it's endothermic and it's disfavorable. So the solution is disfavorable for forming. Okay, if the intermolecular forces in the pure substance is stronger than the intermolecular forces in the solution, then the process is endothermic. And remember, endothermic for enthalpy is disfavorable, so our delta H will be positive. If the intermolecular forces are stronger in the mixture, so in the solution, than the separated species, the enthalpy change is exothermic, and that has a negative delta H, and that's favorable. Okay, so if you have stronger intermolecular forces in your solution rather than in the solute by itself or the solvent by itself, then it's an exothermic process. But for it to have stronger intermolecular forces in its solute and its solvent separately, then it's endothermic and it's disfavorable. So that's for your enthalpy. And then the entropy, the more motion you have, the greater the entropy. So that's usually a little easier to look at. Okay, if you have a gas, again, more disorder, you're going to have a higher entropy. If you have a solid, less disorder, you're going to have a low entropy. So here's an example. Okay, in our gas state, we have weak intermolecular forces. We have the gas molecules spread out. So entropy is favored here because we have more disorder. But enthalpy is a disfavored. And then at our liquid state, we have a more ordered state, so entropy is disfavored, but we have strong intermolecular forces in our liquid, so enthalpy is favored. Okay, so that's okay. You can have one favored and the other not. We're going to talk about what that looks like here in just a second. Anytime we go from a liquid to a gas, though, it's an endothermic process, so that's disfavored and endothermic. It's endothermic, delta H is positive. Okay. So here's the question. If, we said this is all about will the solution form. Okay, that's what we want to know. Entropy and enthalpy play a role in deciding if the solution is going to form. So here's some questions we can ask. Is dissolution enthalpy favored? So basically, is it endothermic or exothermic? If it's exothermic, then yes, it's favored. If it's endothermic, then no, it's not favored. Okay, so let's follow the flow chart up to yes. So let's pretend it's exothermic, so yes, it is favored. And then we look at entropy. Is entropy favored? Okay, remember, there's more disorder, then yes, entropy is favored. If there's less disorder, then no, entropy is not favored. Okay, so if they're both enthalpy favored and entropy favored, then yes, the solute is highly soluble and will dissolve. The solution will form. Okay, if both entropy and enthalpy are favored. But if enthalpy is disfavored, so go down to no. So it's an endothermic process. Enthalpy is disfavored. And then entropy is disfavored as well, so that means we have more order, then the solute is insoluble in the solution or in the solvent. Okay, the solution will not form. Okay, but then we have two more options, right? Those two in the middle. So at the top, the no says solute will be soluble at lower temperatures, and yes, down below it, solute will be soluble at higher temperatures. So if you have let's say enthalpy favored but entropy disfavored, then temperature determines whether the solution will form. And we go to the bottom, we have enthalpy disfavored but entropy favored. Then again, it depends on the temperature whether the solution is going to form. So that's kind of the big thing I want you to know. Okay, if there's both entropy and enthalpy favored, yes, the solution will form. If entropy and enthalpy are both disfavored, then no, the solution will not form. And if we have it in between, we have one of each, enthalpy is favored, entropy disfavored, then it's determined by temperature. Okay, so that's kind of the overall, the gist of what I want you to know with enthalpy and entropy.